The office isn't much to look at in daylight, but tonight it feels suspiciously like it's been borrowed for a different kind of observing run. The blinds are half drawn, turning the window into a patchwork sunshield that keeps the streetlights out and the dark, quiet sky in. On my desk, a ring of coffee cups and old case files forms a kind of golden mirror, each folder tilted at a slightly different angle, catching whatever thin light the lamp is willing to give. The overhead fixture is off, so only that small, focused pool of glow spills across the pages, and everything beyond it falls away into a cool, instrument black shadow. Somewhere out there, the real observatory is floating in that darkness, unfolding its metal petals and collecting ancient, stretched-out starlight. In here, I'm doing the same thing on a smaller scale, spreading those faint signals into notes and diagrams, trying to turn a universe's worth of whispers from the cosmic dawn into something soft enough to fall asleep to. Good evening. If we haven't met yet, I'm Madeline Rowe, an astrophysicist turned private eye, trading telescope time for case files and quiet reports from the edge of the observable universe. Tonight's investigation is a slow one, filed under mirrors and sunshields, under faint galaxies whose light has been stretched thin by 13 billion years of expansion, and finally caught by the James Webb Space Telescope. We're not here to race through headlines or argue about models. We're just going to follow the light itself, from the first small galaxies at cosmic dawn down to the spectra resting on my desk. The file is labelled in calm block letters JWST and the cosmic dawn for sleep. So settle in, let the room grow softer around the edges, and we'll open this folder together, patiently, gently, one calm page at a time. And one small thing before we drift too far into the dark. If slow, case files like this help you unwind, you're very welcome to come back whenever you need a quiet night. If you'd like these to be waiting for you on the evenings when your mind won't quite switch off, a gentle tap on subscribe is more than enough. It tells the office to leave a light on for you. Now, back to the folder and to the telescope that made it necessary. Out beyond the moon, beyond the planets and the bright stars you can see with your eyes, there is a telescope parked in the cold shadow of the Earth. It sits near a place called the second Lagrange point, a delicate orbital balance about 1.5 million kilometers away, where the Earth and Sun's gravity and the motion of the telescope all line up just right. From that perch, the Sun, Earth, and Moon stay more or less in the same direction in the sky. On one side of the observatory, a 5-layer silver sunshield is always turned toward them, like an enormous reflective leaf. On the other side, the side that faces deep space, the telescope opens directly to the dark. The primary mirror is larger than any mirror we've ever launched before, about 6.5 meters across, made of 18 hexagonal segments of beryllium coated with a thin layer of gold. Seen from a distance, it looks like a honeycomb lantern held up to the invisible infrared glow of the universe. The sunshield keeps the warm light of the Sun and Earth out, and the telescope structure radiates its own heat away into space. The metal cools slowly until much of the observatory is just a few tens of degrees above absolute zero. At those temperatures, its own infrared glow becomes faint enough that the ancient light from distant galaxies can stand out against it. That's the observatory as it is now. Inside the folder, the story runs further back. The telescope we call JWST started its life as an idea before Hubble was even launched. Astronomers were already thinking ahead, imagining a successor that could see redder wavelengths into the infrared, where light from the very early universe has been stretched by cosmic expansion. On paper, it began as the Next Generation Space Telescope, more a wish than a machine. Something that could see objects 10 or 100 times fainter than Hubble could, and see them in the infrared instead of the optical. In those early studies, the details were wonderfully vague. Some sketches showed a 10-meter mirror in a high Earth orbit, a colossal monolithic disk of glass that would dwarf any telescope we'd ever built in space. Other concepts flirted with telescopes on the moon, resting on the regolith in permanent shadowed craters where the temperature is naturally low and the infrared sky is very dark. There were debates about whether the mirror should be one solid piece, like Hubble's, or made of segments that could be adjusted. There were arguments about wavelength coverage, about how far into the infrared it should reach, and about what orbit would give the best compromise between thermal stability, communication, and cost. Gradually, like a suspect's description slowly converging from a dozen conflicting witness statements, the architecture narrowed. A telescope in low Earth orbit would be too warm and would see the bright infrared glow of Earth too often. A telescope on the moon would be more ambitious and far more expensive than anyone could realistically build. The L2 point out beyond the Earth offered a good balance, a stable thermal environment, a sky that was always mostly dark on the telescope side, and a manageable communication distance. But if you go that far from home, you have to bring everything you need in one trip. No servicing missions, no follow-up repairs. That constraint shaped almost everything that followed. The mirror had to be big, but launchable. No one was going to build a single 6.5-meter disc and try to cram it into a rocket fairing. So the idea of a segmented primary mirror made of smaller hexagons that could fold up and then unfold in space went from a wild concept study to the baseline design. Beryllium was chosen as the mirror material because it is strong, lightweight, and keeps its shape well at very low temperatures. Each segment would be coated in gold to reflect infrared light efficiently. Behind each segment, tiny actuators would allow engineers to nudge it in position and curvature until all 18 segments behaved like one continuous surface. The infrared ambitions drove the thermal design too. To see faint galaxies at cosmic dawn, the telescope's own infrared glow had to be as low as possible. Earlier, space telescopes had used tanks of cryogenic fluid to keep instruments cold, but those eventually boil away and limit the lifetime. For JWST, the core idea was passive cooling. Keep the warm things, sun, Earth, moon, on one side, and give the telescope a wide, cold view of deep space on the other. That is how the sunshield grew from a modest light baffle into a 5-layer, tennis court-sized kite of reflective and emissive films, each layer slightly offset, radiating heat sideways and away. The fold-out nature of the mirror and sunshield introduced its own knot of problems. Everything had to be hinged, rolled, latched, and tensioned in a precise sequence. Every hinge and cable would be operating once, far from any tool or human hand. Engineers ran deployment tests on Earth again and again, in gravity offloading rigs and clean rooms, looking for anything that could snag, tear, or jam. The more they tested, the more they found small problems to fix. The more they fixed, the more the architecture solidified into the strange spidery shape we recognize now. A spacecraft bus at the bottom, the sunshield stretched out above it, and, riding on the cold side, a segmented mirror and a box of instruments, all exposed to space, with no convenient protective tube. The aim was simple, even if the engineering was not. Build an eye large and cold enough, and instruments sensitive enough to turn faint infrared smudges at the edge of the observable universe into meaningful data. Once you've stared at those diagrams for a while, it's hard not to imagine what it felt like when the real observatory finally left the ground. None of this arrived in space already unfolded. At launch, the telescope looked nothing like the glossy illustrations. It was folded in on itself, the mirror segments tucked in like petals around a bud, the sunshield layers stacked and wrapped, all of it resting beneath the fairing of an Ariane rocket. On launch day, the observatory felt, to the people who had worked on it, less like a machine and more like a very complex promise about to be tested. The rocket rose, the atmosphere thinned, and the fairing opened, dropping away and leaving JWST alone against the darkness for the first time. From that moment, the whole deployment sequence was a kind of mechanical slow motion. The spacecraft cruised away from Earth, following a gentle curve out toward L2. First came the essentials, the solar array unfolding to power the systems, the antennae orienting so that telemetry could stream back. Then the long, careful dance of the sunshield. Pallets swung down, covers opened, booms extended, and the 5 thin layers of film, each as fragile as a cloud of metallic petals, were pulled out, separated, and tensioned like sails. From Earth, the steps arrived as strings of numbers, temperatures changing, motor currents rising and falling, strain gauges settling. If you graph it, the whole thing looks more like a series of heartbeat traces than like the dramatic animation we show in documentaries. Once the sunshield was fully deployed and cooling, the mirror wings could unfold. 2 sets of 3 hexagonal segments swung out from the sides and locked into place. Then the long phase of alignment began, with engineers on the ground nudging actuators micrometer by micrometer, taking star images, adjusting again until 18 separate points of light merged into one tightly focused pattern. What took years to design and months to test on Earth took only weeks in space, but each step landed like its own quiet exhale. Only when the mirror behaved as a single smooth surface and the instruments cooled and focused did the observatory stop being a fragile deployment story and finally become what it was built to be: a cold, steady collector of ancient light. In the margin next to those diagrams, someone has scribbled a little family tree, a reminder that this golden observatory didn't arrive in a vacuum. On another page in the cabinet, someone has sketched a little family tree of space telescopes. At the top is a familiar name, Hubble, the older sibling who has been circling Earth for decades, eyes trained mostly on visible and ultraviolet light. Its mirror is smaller than JWST's, and it lives much closer to home, in low Earth orbit, dipping in and out of the planet's shadow every 90 minutes. From the ground, you can sometimes see it sail overhead as a bright moving star. Engineers have even visited it, riding up on the shuttle to swap out instruments and correct its vision. Hubble's view of the universe is crisp and detailed, especially in optical light. It showed us grand spirals, merging galaxies, star-forming regions knotted with dust. Its deep fields revealed that the apparently empty sky is crowded with galaxies stretching back billions of years. But even Hubble has limits. As you move further into the infrared, the glow of the telescope itself and of the warm Earth below makes it harder to see faint, distant objects. And the most ancient galaxies, whose light has been stretched furthest, slip beyond its reach. Lower down on the family tree is Spitzer, the quieter, more distant cousin. Spitzer was an infrared specialist, a telescope that chased longer wavelengths from its own orbit trailing behind Earth. It began life cooled by a tank of liquid helium, allowing it to see warm dust, cool stars, and the glow of planets. Over time, as the helium boiled away, some of its channels warmed and its vision narrowed. Eventually, its mission ended, and it was gently switched off, left to drift in silence along its orbital path. Spitzer's mirror was much smaller than JWST's, less than a meter across, but it taught astronomers how to design and operate infrared observatories in space. It showed us dusty star-forming regions and the mid-infrared glow of galaxies, and it hinted at planets around other stars by watching tiny changes in starlight as those planets passed in front. If you imagine pointing all three telescopes, Hubble, Spitzer, and JWST, at the same patch of sky, they would each paint a different portrait. Hubble would give you a sharp, detailed view in visible light, blue knots of star formation, redder bulges of older stars, dark lanes of dust silhouetted against the glow. Spitzer would show a softer image in the mid-infrared, more sensitive to warm dust and cooler stars. Structures would be fuzzier, but regions rich in dust and molecules would stand out. JWST, with its larger mirror and colder optics, bridges those views, but pushes them much deeper. In the near-infrared, it can see individual red stars in distant galaxies, trace faint arcs of gravitational lensing, and pull out tiny, high-redshift galaxies that Hubble barely hinted at. In the mid-infrared, MIRI sees dust and molecules in far greater detail than Spitzer did, revealing complex structures in galaxy centers and star-forming regions. For the galaxies of cosmic dawn, those earliest systems whose light has been stretched into the infrared, the difference is even more stark. To Hubble, most of them are invisible. Their ultraviolet glow shifted too far to the red. To Spitzer, they are often too faint and small to separate cleanly from the background. To JWST, they are still faint and delicate, but they are reachable. Tiny smudges in NIR CAM images, delicate spectra in NIR spec data. You can think of it as three sets of eyes on the same universe. One sees the bright colours we're used to, one listens for warm dust and hidden heat, and one, the newest, stares further into the infrared darkness and further back in time than the others could manage. None of them are wrong. Each is simply sensitive to a different slice of the story. And JWST's view of cosmic dawn only really makes sense because the earlier telescopes prepared the way. Hubble taught us where to look and how galaxies behave at later times. Spitzer showed us how dust and infrared light fill in the cooler parts of the picture. JWST steps into the role they pointed toward, taking those techniques and pushing them to the edge of the observable past. If you like family metaphors, you could say that JWST is the younger sibling who moved farther from home, to a darker, quieter neighbourhood, to follow up on hints the older siblings found. When it sends back data from cosmic dawn, it is answering questions that were first asked in Hubble's sharp optical images and in Spitzer's fuzzy infrared glow. The file on my desk simply gathers those answers into one place, letting us read them at our own pace under the small circle of light from the desk lamp, while the rest of the room, and the sky beyond it, stays comfortably dark. All of that engineering care serves a particular scientific ambition: The notes in this folder shift from diagrams of mechanical hinges and mirror segments to sketches of something older, the universe itself, in its first few 100 million years. Cosmic dawn is the name we give to the time when the first generations of stars, galaxies, and black holes began to form and light up the universe. Before that, there was the afterglow of the Big Bang, the cosmic microwave background, a fog of radiation that filled space when the universe was only about 380,000 years old. After that glow thinned and stretched into microwaves, matter and radiation decoupled, and the universe entered the so-called Dark Ages. Gas, mostly hydrogen and helium, cooled and flowed along the filaments of the invisible dark matter web, gathering into deeper and deeper gravitational wells. Eventually, in the densest regions of that web, gas clouds became unstable. They collapsed and fragmented, forming the first stars. Those first stars were probably very massive and very bright. They burned through their fuel quickly, pouring out ultraviolet light that ionized the gas around them and ending their lives in spectacular supernova explosions. Groups of stars gathered into proto-galaxies, clumps that would, over time, grow into the galaxies we see later. Heavy elements forged in the hearts of those first massive stars, carbon, oxygen, iron, began to sprinkle into the gas between them. The universe, which had been chemically simple, started to acquire a more interesting periodic table. All of this happened long ago and far away. Light that left those early stars and galaxies when the universe was a few 100 million years old has been travelling for more than 13 billion years to reach us. As it moves through an expanding universe, the light's wavelength stretches too. Photons that began as ultraviolet or even higher energy radiation are now stretched into the infrared. By the time they arrive at L2 and strike JWST's mirror, they are too red for our eyes to see and too long wavelength for Hubble's detectors to handle efficiently. That stretching is what astronomers call redshift. You can think of redshift as a record of how much the universe has grown while the light was in flight. The larger the redshift number, the farther the light has travelled and the further back in time you're seeing. High redshift galaxies are cosmic fossils. They show us what galaxies were like when the universe was still very young. JWST is tuned to catch their stretched out light, but even for a telescope with a large mirror and cold instruments, these early galaxies are incredibly faint. They're not big spirals you can admire in a single glance. In deep JWST images, they appear as tiny smudges, a few pixels across, hiding among more numerous foreground objects. Finding them is its own quiet detective work. Astronomers begin with deep images, taken through different filters. Each filter passes a range of wavelengths, like a coloured window. Early galaxies have characteristic colours in this filter space because of how neutral hydrogen absorbs their light. At wavelengths shorter than a certain limit, hydrogen absorbs most of the photons. At longer wavelengths, the light gets through. In a universe that is expanding, that dividing line slides to redder and redder, filters for more and more distant galaxies. So astronomers search for sources that are visible in redder filters but simply vanish in bluer ones. They are bright in some images, completely absent in others. This pattern marks them as dropouts, candidates for high redshift galaxies whose ultraviolet light has been carved away by hydrogen along the line of sight. Some of the richest hunting grounds for these candidates are fields that include massive foreground galaxy clusters. Those clusters act as gravitational lenses, bending and magnifying the light of background galaxies. In the images, you can sometimes see delicate arcs and stretched smears that are distant galaxies, distorted and brightened by the cluster's gravity. Behind them, in the magnified regions, even fainter galaxies from cosmic dawn can sometimes be teased out. But candidates are only the first layer of the case file. To really know how far away these galaxies are and what's happening inside them, astronomers need spectra. A spectrum is what you get when you take a galaxy's light and spread it out by wavelength, like pulling a piece of music apart into its individual notes. Instead of a single brightness value, you get a curve, bright here, faint there, with spikes and dips and steps. Each of those features tells a particular story. Some spikes are emission lines, produced when gas clouds around young stars or black holes are excited and then radiate at specific wavelengths. Some dips are absorption lines, where starlight has passed through cooler gas or dust and lost certain colours along the way. Some steps are breaks, where a whole range of wavelengths has been suppressed, often because hydrogen is blocking high-energy photons. Because the universe is expanding, all of these patterns slide to longer wavelengths for more distant galaxies. By measuring where they now appear in the spectrum, astronomers can deduce how much the light has been stretched, and therefore how far back in time they're looking. On JWST, the jobs of imaging and spectroscopy are shared between a small cast of instruments, each with its own personality. There's NIRCam, the near-infrared camera, which acts like the wide-field scout. It takes deep images in multiple filters, the ones that reveal those dropouts and gravitationally lensed arcs. If you've seen a JWST deep field with hundreds of tiny coloured galaxies, you've seen NIRCam's work. Then there's NIRSpec, the main near-infrared spectrograph, which is more like the interrogator. Using a clever array of tiny shutters, it can take spectra of many galaxies at once, opening a little window wherever there's a faint smudge to examine and keeping others closed. In a single observation, NIRSpec can record the fingerprints of dozens of candidates, turning colours into distances and physical properties. Out at longer wavelengths sits MIRI, the mid-infrared instrument, colder and quieter than the others, thanks to its own dedicated cryo-cooler. MIRI is the slow, patient listener, tuned to cooler dust and more deeply embedded structures. It helps trace how starlight heats dust and how that dust glows in the mid-infrared, rounding out the picture of star formation and galaxy growth. And always, hovering in the background, is the fine guidance sensor and its partner instrument, making sure the telescope's aim stays rock steady, keeping stars pinned to the same detector pixels so that tiny variations in light can be trusted. Together, these instruments let JWST act not just as a big mirror, but as a small team of specialists, one finding the targets, another dissecting their light, another listening for the faint heat of dust. All of this complexity serves a simple goal: turn faint, stretched photons from the early universe into detailed spectra we can interpret. Some of the most important features in those spectra are breaks. One is the Lyman break, where neutral hydrogen eats almost all the photons above a certain energy. Another is the Balmer break, linked to the cumulative effects of older stars in a population. Because of redshift, these breaks appear at different observed wavelengths, depending on distance. By spotting where a spectrum suddenly steps up from almost zero to measurable light, and by measuring the positions of emission lines around that step, astronomers can estimate both distance and the underlying population of stars. With enough spectra in hand, patterns start to emerge. One of the striking results from JWST's first years is that many early galaxies seem brighter or more efficient at forming stars than simple models anticipated. We see systems, only a few 100 million years after the Big Bang, that are already forming stars at a furious pace. Their emission lines are strong. Their ultraviolet-derived star formation rates seem high. In some analyses, the inferred stellar masses are surprisingly large for such young ages. It's as if the universe hit the ground running. But interpreting these galaxies is subtle. If a galaxy has recently gone through a burst of star formation, the light from young, massive blue stars will dominate. They can temporarily make the galaxy look much more massive than it is, because older, redder stars contribute less to the light, even if they contribute more to the mass. Different assumptions about how star formation rises and falls over time, whether it is smooth, bursty, or intermittent, can change the inferred masses and ages. Dust complicates things further, reddening the light and hiding some regions from view. So part of the ongoing work is to figure out how much of this bright cosmic dawn is truly surprising, and how much reflects our evolving understanding of how to read these spectra. At the same time, the universe as a whole is going through another transformation. In the very early stages, the space between galaxies, the intergalactic medium, is filled with neutral hydrogen. That gas is very good at absorbing high-energy ultraviolet light. As more stars and galaxies form and pour out UV photons, they gradually ionize that hydrogen, knocking electrons free. Around each group of galaxies, a bubble of ionized, more transparent gas grows. Over hundreds of millions of years, these bubbles expand and merge until most of the intergalactic hydrogen is ionized. This era is called re-ionization. JWST helps map this process by studying galaxies at redshifts where re-ionization is still underway. By comparing how their light is absorbed at different wavelengths and by counting both bright and faint galaxies, astronomers infer when most of the hydrogen became ionized and which populations of galaxies contributed the most to the ionizing photon budget. Inside those young galaxies, stars are doing more than just shining. The very first stars likely formed from almost pristine hydrogen and helium. When they die in supernova explosions, they forge heavier elements. Astronomers call all of these metals, even when they're things like oxygen and carbon. JWST's spectra allow measurements of these metals in early galaxies. Some systems show extremely low metallicities, heavy element abundances only a small fraction of the sun's. They're not truly primordial, but they're close to the environments in which the first stars would have lived. By examining the ratios of different elements, how much oxygen compared to iron, for instance, astronomers can infer the kinds of supernovae that enriched the gas and how quickly enrichment occurred. It's like reading the chemical family tree of a galaxy. While all of this stellar alchemy is going on, some regions of the universe are growing something even more extreme: black holes. We know that by less than 1 billion years after the Big Bang, there are already quasars, galaxies whose centers are lit up by supermassive black holes with masses millions or billions of times that of the Sun. The existence of such heavy black holes so early means their seeds must have formed and grown quickly. JWST contributes by finding not only very bright quasars, but also fainter active galactic nuclei. In deep fields, astronomers have picked out compact, very red sources whose colours and spectra hint at buried or heavily obscured black hole activity. Some of these sources, tiny and dense in the images, have been nicknamed little red dots. They're not showy in the way classic quasars are, but they may represent a more common phase of early black hole growth. If many small galaxies spend some fraction of their lives in this state, compact, dusty, with quietly feeding black holes at their centers, that could help explain how the giant black holes we see later grew so quickly. We still don't know exactly how the initial black hole seeds formed. They may have started as the remnants of very massive stars, collapsing into black holes tens or hundreds of times the mass of the Sun, and then growing via accretion and mergers. Or, in some rare conditions, gas may have collapsed almost directly into heavy black holes, skipping normal star formation. JWST can't watch those seeds form in real time, but by counting active galactic nuclei, measuring their inferred masses, and mapping their environments, it can test which scenarios fit best. If all of this starts to feel like too many moving parts, we can let the view narrow. Imagine sitting here in the office with a single printed spectrum in front of you. The lamplight falls across a graph. Along the bottom axis is wavelength, running from shorter to longer. Along the vertical axis is flux, the amount of light arriving at each wavelength. Our galaxy from cosmic dawn is traced as a jagged line across this plot. You can picture that line as a piece of handwriting. Each bump and dip, each sharp spike, is a letter in the script. If you follow that line backwards in your imagination, you can trace each point to its origin as a photon. A photon leaves a young galaxy more than 13 billion years ago, born in the hot surface of a massive star or in a glowing gas cloud, excited by that star's light. It travels through the galaxy's own gas and dust, perhaps slipping past a cluster of forming stars or skimming the outskirts of a supernova remnant. Then it escapes into intergalactic space, beginning its long journey along the expanding fabric of the universe. As space stretches, the photon's wavelength stretches too, changing from ultraviolet to optical to infrared. Billions of years pass, structures form and grow elsewhere. Our own galaxy assembles, the sun forms, planets congeal. Life appears and starts to wander about the sky. All the while, that photon keeps going, its path bent only slightly by the gravity of clumps of matter it passes near. Eventually, the photon approaches a small, cold, gold mirror orbiting near L2. From the photon's point of view, the mirror is racing toward it at just the right angle. It strikes one of the hexagonal segments, reflects towards the secondary mirror, then down through the telescope's optical system into one of the instruments. Inside the instrument, it hits a detector, a tiny patch of semiconductor material cooled to low temperatures. Its energy releases a small charge, a whisper of current. That signal is added to all the others that arrive during the exposure, building up a pixel's brightness. Later, the detector is read out. The charges are converted to numbers, wrapped into data packets, and sent as radio signals back to Earth. They're received by large dish antennas, routed through networks, and stored in servers. Software pipelines subtract detector noise, correct for instrument quirks, calibrate wavelengths and fluxes, and finally reconstruct an image or a spectrum. At the end of this chain, somewhere on Earth, someone opens a file and sees a line on a graph. That line, the one you're picturing on the desk, is the end of a journey that began before our planet existed. Now, if you look closely at that line, you notice its shape. On the left, at shorter wavelengths, it lies almost flat against the baseline. Neutral hydrogen along the line of sight has absorbed most of the high-energy photons there. Then, at a particular wavelength, the line steps upward. That sharp edge is the shifted Lyman break, the point where hydrogen stops blocking so efficiently. Beyond that, the continuum rises and then slopes gently downward as wavelength increases. Superimposed on this gentle slope are spikes, emission lines from hydrogen, oxygen, and other atoms in gas clouds lit by young stars. Between the spikes, the line wiggles and dips where stellar atmospheres and dust have carved out features. Even if you don't remember the names of the lines, you can think of each spike as a street lamp along the road, a place where the galaxy is shouting a little louder in a specific colour of light. From this single spectrum, an astronomer can infer the galaxy's redshift, its rough star formation rate, clues to its metallicity, and hints about its dust content. If there were a growing black hole at the centre, some of the emission lines might appear broader, smeared out by gas orbiting at high speed. The continuum might tilt differently, rising more at shorter wavelengths where the accretion disk contributes. In your mind, you can imagine swapping the spectrum in front of you for one of those. The spikes are still there, but some are wider, and the baseline is brighter and smoother. That's what a high redshift quasar might look like in this language. The same alphabet, but a different handwriting. Elsewhere in the folder, there might be a contrasting spectrum from a tiny, extremely metal-poor dwarf galaxy. In that one, many of the metal lines are faint or missing. The continuum is dominated by young stars, but the chemical signatures are sparse. Two galaxies, similar in distance, but very different in their histories, revealed by the shapes of their lines on the page. Zooming out from the desk again, you can imagine stacking many such spectra, each one representing a single galaxy at a particular time. Over decades, astronomers have kept informal tallies of the most distant galaxies and quasars known, each one marked by its redshift. Early on, the record holders were relatively nearby by today's standards. People were just realizing that many of the fuzzy nebulae in the sky were in fact separate galaxies, and measuring their redshifts involved painstaking spectroscopy on photographic plates. Later, with radio astronomy and large optical telescopes, quasars took over the record. Because they are so luminous, they can be seen at enormous distances. The most distant known objects became quasars rather than normal galaxies. As instruments improved and detectors became more sensitive, the frontier in redshift crept higher. Ground-based telescopes with mirrors 8 to 10 meters across, combined with the Hubble Space Telescope, pushed confirmed galaxy redshifts into the realm where re-ionization was still underway. Deep imaging, color selection, and follow-up spectroscopy revealed galaxies at redshifts of 6, 7, and beyond. By the time JWST launched, we already had a few galaxies confirmed at very high redshifts, and hints of even more distant candidates. But the data were often noisy. Key lines lay at wavelengths that were hard to observe from the ground. JWST's arrival shifted the balance. With its infrared coverage and sensitivity, it could catch the crucial breaks and emission lines for galaxies even further back in time. Within its first years, it confirmed galaxies with redshifts above 10, corresponding to times when the universe was only a few 100 million years old. Different teams sometimes proposed different objects as the current record holder, depending on the strictness of their criteria and the quality of the spectra. But the deeper point is that the record is no longer a single isolated object. JWST is filling in a population, turning 1 or 2 lanterns at the end of the road into a sparse but meaningful string of lights. From where you're lying, all of that can simply be a gentle mental scale. Nearby galaxies at low redshift sit at one end. Quasars and galaxies in the re-ionization era occupy the middle. And way out at the far end are these tiny JWST discoveries from cosmic dawn, all bound together by the same idea: light that has been stretched by the expansion of space. You don't need to remember the numbers, only that each new detection extends our view a little further into the past. The file doesn't stop with the redshift list. There are a few pages devoted to portraits of specific discoveries, each one a small character study in the broader story. One page shows a compact reddish point in a JWST deep field, sitting among lensing arcs and foreground galaxies. Underneath, a note. Likely AGN, heavily obscured, candidate little red dot. The spectrum shows strong, somewhat broadened emission lines and a rising continuum. Another page shows a tiny galaxy magnified by a foreground cluster, its light stretched into a faint arc. The analysis notes highlight its low mass and extremely low metallicity. It is, chemically, a throwback, a system that has undergone very little enrichment, a laboratory for studying star formation in conditions not far removed from the first stars. A third page shows a small, slightly elongated galaxy in a deep field, with measured redshift above 10. It isn't particularly dramatic in appearance. Its significance lies in timing. It is one of the earliest known examples of a galaxy already in place, only a few 100 million years after the Big Bang. Each of these objects is just a point in a diagram, a squiggly line in a spectrum, a handful of data files in a server. But in the story you're hearing, they can be three quiet faces in the crowd. A compact red ember hinting at a buried black hole. A chemically primitive dwarf tracing early enrichment. A record-breaking distant galaxy anchoring the timeline. If your mind would like something more visual and less technical for a while, you can drift into a thought experiment. Imagine, just for a moment, what the sky might look like from inside a galaxy at cosmic dawn. We don't know all the details, and we don't have to. This is just a soft picture to carry you further towards sleep. Picture a young galaxy, smaller than the Milky Way, but bursting with star formation. Gas clouds thread through it, dense in some regions, more diffuse in others. Massive stars cluster along the spiral of the gas, burning hot and blue. They pour out ultraviolet light, carving bubbles of ionized gas around them. Some of these stars are on the brink of explosion. Others have just lit up. Imagine a vantage point somewhere in this galaxy, a dusty plateau, a cool cloud top, the surface of a rocky world, if you like. The exact setting is yours. Above you, the galaxy's disk arches across the sky as a hazy band of light, more irregular and knotted than the Milky Way you might see from Earth. Star clusters punctuate it like bright knots. Here and there, glowing nebulae hang like coloured lanterns, where gas is being ionized by young stars. Closer to you, a supernova may briefly outshine everything else, then fade over weeks and months, leaving behind an expanding shockwave and a compact remnant. In the distance, somewhere toward the centre, there might be a region that glows differently, where gas is falling toward a growing black hole. To your eyes, it might just be another bright patch. To a spectrum, it would be a distinctive flare of certain lines. Beyond your galaxy, the intergalactic medium is still partly neutral. In some directions, the universe is already transparent to ultraviolet light. In others, hydrogen still blocks those photons. If you could see in those energies, you'd notice that the background sky is mottled with pockets of transparency and opacity. as if parts of the darkness were still carrying a faint fog. Over cosmic time, those patches will change as bubbles of ionized gas expand and merge. From your imagined vantage point, though, it is simply a busy, luminous sky. The noise of winds, supernovae, and radiation doesn't reach you here. Only the idea of it does. Back in the present, the office is quiet. The telescope outside the window is invisible to your eyes. It's just a thought, a steady presence hanging beyond the atmosphere. On the last pages of the file, the notes turn reflective. They talk about tensions between early JWST findings and the simplest galaxy formation models, galaxies that seem too bright or too massive too early, black holes that seem to have grown very quickly, re-ionization histories that need to reconcile galaxy counts, quasar observations, and measurements of the cosmic microwave background. Some headlines have tried to turn these tensions into drama, suggesting that JWST has broken cosmology. Most of the people actually working with the data are more cautious. The broad framework of a universe filled with dark matter and dark energy still fits a vast range of observations very well. What JWST is mostly doing is shining a sharper light on the messy details of how galaxies assemble within that framework. A lot of the tension lives in the small print, in how star formation histories are modelled, in assumptions about dust, in how complete a survey is, in how you translate light into mass. As more data accumulate and different teams cross-check one another's methods, some of the early extreme interpretations have already softened. Candidates for extraordinarily massive galaxies have been revised downward after more careful modelling. Other peculiar objects have held up under scrutiny and are pushing theorists to revisit their assumptions about feedback, gas accretion, and the efficiency of star formation in small halos. This back and forth is part of how science normally behaves, especially when a new instrument opens up a previously inaccessible regime. The other half of that conversation doesn't happen at the telescope at all. It happens in computers, inside little artificial universes that try to keep up with what JWST is seeing. Far away from the telescope's orbit and from this small office, there is another kind of observatory at work. It doesn't have a mirror or a sunshield. It lives in rows of humming racks inside data centers and computing facilities, where fans move warm air and blue indicator lights blink in patterns only a few people ever think about. On those machines, astronomers and physicists run simulations of the universe, numerical experiments where the laws of gravity, fluid dynamics, and radiation are turned into equations that a computer can step through in time. In one of those simulations, the early universe begins as a nearly uniform fog. Tiny fluctuations in density, imprinted in the cosmic microwave background, grow slowly under the pull of gravity. In the code, dark matter is represented by countless particles or cells, moving and clumping according to simple rules. Gas follows along, cooling, heating, flowing into the potential wells. Time is advanced in small steps, thousands or millions of increments, each one updating the positions, velocities, and temperatures. You can imagine it as a three-dimensional box, maybe a few tens of millions of light years on a side, wrapped in periodic boundary conditions so that anything leaving one face of the box re-enters on the opposite face. Inside this box, if you run the simulation forward, structure begins to appear. Small halos of dark matter condense first, then merge into larger halos. Gas falls into those halos, compresses, and when certain conditions are met, some of that gas is turned into stars in the code. Those stars, in turn, release energy into the surrounding gas and sometimes drive outflows. Supernovae deposit metals into the medium, changing how quickly future gas can cool. Black holes may be seeded in dense regions and allowed to accrete, adding their own feedback. It is, in miniature and speeded up, the same process we've been talking about, cosmic dawn unfolding. But in the simulation, you can see every part of it at once. You can pause the universe at any moment and look at the distribution of gas, stars, metals, and dark matter. You can rewind and replay. You can run the same initial conditions with slightly different recipes for star formation or feedback and see how much difference it makes. At first glance, it might seem as though these simulated universes could simply replace observations. Why struggle to pull faint spectra out of the noise when you can just scroll around inside a beautifully rendered, perfectly known model? But simulations are built on assumptions and approximations. The resolution is finite. Small-scale processes have to be sub-grid, represented by simplified rules. Feedback from stars and black holes is complicated and not fully understood. Cooling and heating depend on many factors, so simulations and observations serve different roles. One creates possible universes according to our best guesses. The other shows us the universe we actually live in. The useful part is when you compare them. For JWST and cosmic dawn, that comparison is becoming especially rich. From simulations, you can predict things like how many galaxies of a given brightness should exist at a certain redshift, how clustered they should be, how quickly metals should build up, how many black holes should have grown above a certain mass. From JWST, you measure the same kinds of quantities: luminosity functions, metallicity distributions, the incidence of active galactic nuclei, the timing of re-ionization. If the two match reasonably well, you gain confidence that your recipes are capturing the essence of the physics. If they don't, you have clues about where the recipes need changing. Maybe star formation is more bursty than you assumed. Maybe feedback is more efficient. Maybe black holes grow faster under certain conditions. Each mismatch is less like a failure and more like a handwritten note in the margin. Check this assumption. Try a different feedback model. Look again at the faint end of the luminosity function. You can imagine, if you like, that for every JWST deep field, there is a matching virtual deep field inside some computer's memory. The simulated field is populated with galaxies whose properties are known exactly in the code. The real field is populated with galaxies whose properties we infer from noisy spectra and images. Astronomers put plots from one beside plots from the other and compare the shapes of the curves. They adjust the simulation, rerun it, compare again. Over time, the virtual universes begin to resemble the observed one more closely, at least in broad strokes. There will always be differences. No simulation can capture every process in full detail, and no telescope can see every object without bias. But together, telescopes and simulations sketch out a more complete picture than either could alone. The telescope tells us what is there. The simulations suggest how it might have come to be. In a way, JWST is whispering to these universe-in-a-box experiments, sending back constraints that say, here is how bright the galaxies really are, or here is how fast metals appear, or here is how common early black holes seem to be. The simulations reply by saying, here is what had to happen in our equations for this to be true. When both sides agree, you get a little surge of quiet satisfaction. When they disagree, you have something new to think about. From your side of the speakers, you don't have to worry about the specific codes or parameter choices. You can just hold onto the idea that there is a second observatory running in parallel with JWST, not in space, but in silicon. One collects photons from cosmic dawn. The other collects floating point numbers from evolving equations. Between them, they narrow down the range of possible histories the universe could have had, until what remains is a story that fits both the data and the laws of physics as we understand them. Tonight, that story is still a draft. But it's a draft with much sharper ink than we had before. And while you sleep, both telescopes and simulations will keep working, refining the picture, so that the next time you open this folder, the universe at cosmic dawn will be just a little less mysterious and just as quiet. From the outside, it can sound like arguments. From the inside, it feels more like sanding the rough edges off a sculpture. Measurements are improved. Models are adjusted. Pieces that don't fit are either reshaped or set aside until new data arrive. JWST is a powerful tool in that process, but it isn't the whole process. It will eventually hand the baton to other observatories. In the near future, a mission called the Roman Space Telescope will map huge swaths of the sky in the infrared, complementing JWST's deep, narrow gaze with a wide, shallower survey. On the ground, extremely large telescopes with mirrors 30 meters across are being built. Their adaptive optic systems will sharpen their views of galaxies and quasars and allow detailed follow-up that even JWST cannot do alone. Further down the line, people are already sketching ideas for telescopes that could see even further into the ultraviolet, or in other bands, tying together more of the cosmic story. So JWST is not the last word on cosmic dawn. It's a crucial chapter. It takes us from rough guesses to detailed measurements, from isolated marginal detections to rich, multi-wavelength datasets. The story will continue to evolve as new instruments come online and as the current troves of JWST data are mined more deeply. For tonight, though, the telescope can rest in your mind as a single, steady idea. A golden, segmented mirror floating in the cold, its sunshield turned toward the sun, its dark side turned toward the deep past. A stream of faint photons from cosmic dawn is hitting that mirror even now, being fed into instruments, converted to electrons, turned into numbers, and archived. Some of those numbers are being poured over in real time. Others will sit in archives for years before someone thinks to ask a new question of them. Some fraction of that work flows indirectly into the words you're hearing now. What you might keep, if you like, is a gentler message beneath all the details. Even at the earliest times we can see, the universe is already creative. Galaxies take shape, stars ignite, elements heavier than hydrogen are forged, black holes grow, light escapes into the surrounding medium, marking each of these events with a trace we can, much later, learn to read. Billions of years after some of that light left its source, it ends up in a carefully built telescope at L2. After being turned into data, some of those photons become lines on a page, plots on screens, and, on evenings like this, a story to fall asleep to. If your eyes are heavy now, you're exactly where you're meant to be. You can let the specifics blur. The telescope will keep working, the spectra will keep arriving. The universe will continue its patient expansion, turning ultraviolet flashes into long, soft infrared waves. I'll close the file on JWST and the cosmic dawn for tonight, and slide it back into the cabinet, between neutrinos and the invisible sky, and dark matter, dark energy. The lamp on the desk can dim in your thoughts until it's just a warm glow at the edge of sleep. Thank you for keeping me company on this quiet shift. Rest well. When you need another calm investigation, this office and the sky beyond it will still be here, waiting.